Measuring current as the voltage changes across other components. So we can put different components in. So this is our circuit again. The variable resistor is already in here. We know that in series we have our ammeter and in parallel we have our voltmeter. And so you can put your component in there, vary your voltage, measure your current and plot a graph. And the components that you have to learn are the ones that you have to learn the graphs of are a bulb or filament lamp, and its symbol is that. You also have to do something called an NTC thermistor. It's not unlike a resistor, but it has a very strange looking line through it with a very flat part in the end. And the third one that you need to know, as well as a wire, is a semiconductor diode, and it's got a circuit, a diagram like this. And it's a triangle with a line, and then it's got a circle drawn around it. So if you were asked to draw a circuit to measure the current as the voltage changes across a diode, you would draw the circuit, but you put the diode symbol in there, or the bulb if that was the case, or the NTC thermistor if that was the case. Right, these are the 4 current voltage graphs. We call them characteristic graphs that you have to know. So I'll show you what they are first of all, and then I'll explain each one. I've already explained the ohmic conductor, which is a wire or a resistor, and it's a perfect straight line which goes through the origin. Number 2 is a filament lamp. Now you can see with a filament lamp that it isn't a straight line, and actually it's a curve whose gradient gets less and less as it goes on. Number 3 is a negative temperature coefficient thermistor, and it's exactly opposite to a filament lamp, and it would be fairly easy to get those two mixed up. Its gradient is actually increasing as you go on. And the last one is a semiconductor diode, and it has probably the most distinctive shape. It has got no current flowing for these negative voltages. So those are negative voltages and these are positive. No current flowing. The line is right along the axis, and it takes until it's usually about 0.7 volts before it actually starts to allow current to flow through it in the other direction, and then it increases quite sharply. So the question says, which of these components obeys Ohm's law? The wire, of course, obeys Ohm's law, and the semiconductor diode to some extent after 0.7 volts. So after 0.7 volts, it will obey it. Now I'll explain 2, 3 and 4. A filament bulb. Sometimes you're asked, why is the shape of the graph the way it is? And the reason is that as you increase current, as you increase current in a filament bulb, the filament starts to heat up. So if you remember, Ohm's law only applied whenever the temperature remained constant. The filament heats up. And as the filament heats up, this increases its resistance. So the hotter it is, the more resistance. And therefore, the graph is a curve. If I just go back here a minute just to show you, if you had to calculate resistance from your ohmic conductor graph like this, no matter where you take a value of V, because it always falls in a straight line, V divided by I will always give you the same resistance. So you're getting a constant resistance from this. But from this one here, you can see there that for low values of V, you have high values of I. But as you go on, you don't get, the values of I don't increase by an awful lot more. And so you're dividing a big voltage of V by a relatively small value of I and getting a bigger resistance as it heats up. And therefore, you can do a calculation on a question and just check that, but that's the reason why the graph is a curve. The next component is a negative temperature coefficient resistor, and this does the opposite to the filament bulb. So, as you increase I, in the NTC thermistor, the thermistor heats up. But the effect of that is, this time, it actually decreases the resistance of the thermistor. Now, an NTC thermistor is made, sorry, I have the word resistor there, I'm just realising that's wrong. It's a thermistor. So it's a negative temperature coefficient thermistor. And it decreases resistance. So as you increase the current in a thermistor is made up of a semiconductor material, and when you increase the current flowing through it, this decreases its resistance. And therefore, as V increases there, more and more current is allowed to flow, and that gives the graph a curve shape again, but this time the curve is in the opposite direction to the bulb, which goes that way there. So the graph is also a curve. Now those are the two that you may get mixed up in and that you really, really need to learn. Number 4 is something called a semiconductor diode. This is its symbol here. And what happens is whenever you connect a semiconductor diode into a circuit, there's a right way and a wrong way to connect it. If you connect it into the circuit the wrong way, I'll explain why this is the wrong way here, then no current flows. There's the direction of conventional current, and when a diode is connected in the right way, that arrow should go in the same direction as the direction of conventional current. So this arrow is pointing towards it, so therefore this is the wrong way. We call that reverse bias. I might just scan in a wee bit there for you. Okay, so that's called reverse bias, and no current flows. On the second part of the graph then, whenever you connect your diode in the right way around, so the arrow is going the same direction as conventional current, then you will find that you have current flowing, but only after about 0.7 volts. So it only conducts after 0.7 volts when it's in forward bias. You don't really need to know those words, but that's the way it's described. And that just means that you're connecting it in one way or another. So in other words, a diode only allows current to flow in one direction. Whenever you put it in the other way, it won't allow current to flow in that direction. So it only conducts after 0.7 volts in a forward bias. Now, a couple of years ago in an exam paper, they gave you a graph. They gave you 3 graphs to identify. The first one was a straight wire, which was fine, but there were 2 more, and one was a curve like this, and one was like this, but it had this part missing. And it was hard to tell the difference between the 2 of those. They weren't that dissimilar looking, but the fact that this had no current up until about 0.7 volts was a big factor in deciding that that was definitely a semiconductor diode.